Hey guys. I am Haiii. I am a student who is focusing on graph theory. Today I will have a meeting with Mr. Hernandez. Today's discussion is about maximum flow minimum cut. Keep watching until it's finished. Now I'm waiting for the bus to go to Mr. Hernandez. Keep watching guys. Good morning Mr. Hernandez. I'm sorry to disturb your time. Can we discuss material on graph theory today? About maximum flow minimum cut?
Good morning. No problem Haiii, sure. Do you know what a theory is?
In mathematics, graph theory is the study of graphs, which are mathematical structures used to model pairwise relations between objects. A graph in this context is made up of vertices, also called nodes or points, which are connected by edges, also called links or lines.
Good. Because you understand enough of that, now we will discuss maximum flow minimum cut. In optimization theory, maximum flow problems involve finding a feasible flow through a flow network that obtains the maximum possible flow rate. The maximum flow problem can be seen as a special case of more complex network flow problems, such as the circulation problem. The maximum value of an ST flow, that is, flow from source S to sink T, is equal to the minimum capacity of an ST cut, that is, cut severing S from T in the network, as stated in the max flow min cut theorem. It was developed by L. R. Ford, Jr. and T. R. Fulkerson in 1956. A pseudocode for this algorithm is given below. Inputs required are network graph, source node and sink node. Maximum flow problems involve finding a feasible flow through a single source, single sink flow network that is maximum. Let's take an image to explain how the above definition wants to say. Each edge is labeled with capacity, the maximum amount of stuff that it can carry. The goal is to figure out how much stuff can be pushed from the vertex S source to the vertex T sink. Maximum flow possible is 23.
I see. What about minimum cut?
In graph theory, a minimum cut or min cut of a graph is a cut, a partition of the vertices of a graph into two disjoint subsets, that is minimal in some sense. Variations of the minimum cut problem consider weighted graphs, directed graphs, terminals, and partitioning the vertices into more than two sets. The figure on the right is a network having the value of flow of 7. The numerical annotation on each arrow, in the form x/y, indicates the flow x and the capacity y. The flows emanating from the source total 7, 4 plus 3 equals 7, as do the flows into the sink, 3 plus 4 equals 7. The vertex in white and the vertices in gray form the subsets S and T of an ST cut, whose cut set contains the dashed edges. Since the capacity of the ST cut is 7, which equals the value of flow, the max flow min cut theorem indicates that the value of flow and the capacity of the ST cut are both optimal in this network. Note that the flow through each of the dashed edges is at full capacity. This is the bottleneck of the system. By contrast, there is spare capacity in the right-hand part of the network. In particular, the flow from node 1 to node 2 need not be equal to 1. If there were no flow between nodes 1 and 2, then the inputs to the sink would change to 4/4 and 3/5. The total flow would still be 7, 4 plus 3 equals 7. On the other hand, if the flow from node 1 to node 2 were doubled to 2, then the inputs to the sink would change to 2/4 and 5/5. The total flow would again remain at 7, 2 plus 5 equals 7.
Thank you for your time Mr. Hernandez.
You're welcome Haiii.